Yeah.
Okay, let's get started, please. Okay, let's get started, please. So, we were just finishing up the great properties of uniformly convergent sequences, right? And so we're going to have a little bit of a digression, which is the construction of a continuous nowhere-differentiable function. Okay, so the first such function was created by Weierstrass, and apparently it outraged many other mathematicians at the time. They called it like an abomination, no, a monstrosity, a crime against common sense. Something along these lines. It was Poincaré said something along these lines, that it was a monster and a crime against common sense to have such a function. But Weierstrass created it, and yeah. As a side remark, I was once asked at a party of mathematicians. It was my first job as a mathematician and as a professor, and I went to a party, and one of the mathematicians there said to me, "Hey, so who is the greatest 19th century analyst?" And I was like, I don't know. You know, it was my first job. Inside I was thinking Weierstrass, but I was kind of too embarrassed to say it. What if it were wrong, right? But this guy, called out to other people. It's like, hey, this guy doesn't know who the greatest 19th century analyst was. Then he told me that it was Weierstrass. So I should have trusted my instincts. So just in case you too get bullied by some other mathematician, Weierstrass is the greatest of 19th century mathematicians, analysts. Okay, so so here's how we're going to make it. So we're constructing a continuous function that's nowhere differentiable, right? If I said, give me a continuous function that's not differentiable at a single point, you could probably do that for me, right? One example would be the absolute value function, right? That's continuous. It's not differentiable at the origin, right? And so what we're going to do is we're going to use that. So we're going to create a function basically using that function. So this is different from what Weierstrass did, but it's along the same lines. Okay, so let's just look at the absolute value function between -1 and 1, and we're going to call that thing phi. Okay, so phi is going to be the absolute value function as long as x lies between -1 and 1. Okay, and then we're going to extend it. So extend phi to all of r periodically. Okay. So we create a function of period 2, right? So f of x plus 2 is going to be defined as f of x. Okay, so you see what's going to happen, right? This is just going to start. It just starts repeating, right? It just starts repeating like this, right? You make a periodic function. Okay. So and then what we do is we're going to take different scalings of this function. So we're going to you're going to take phi of 4x, phi of 4 squared x, phi of 4 cubed x, and so on and so forth. Right. So you speed up time by powers of 4. Right. So phi of 4x, right, is going to look like this. Right. It'll be right. So all right, I'm going to erase this here, right? Right, so 1, 2, 3, 4, right? Right, so we compress time by 4, right? And so it looks like this, right? Between 1 and -1 is -1. Right? And you see that this thing has more points of non-differentiability, right? So it's got it's got the same number, right? There are infinitely many points of non-differentiability, but they're sort of denser now, right? They're 4 times as dense, right? And we keep on doing that over and over, creating 4 times as dense, 4 times as dense, and so on and so forth. And then we're going to add all those things together. Okay. Now that's not right. We don't want to add them together, because if we add them together, we're going to get a divergence, right? We're going to get a lot of divergence, right? Because there are a lot of points where you've got, like, you're not sure about if this is going to converge or not. So instead, what we do is we multiply, right? So we're going to take all these things where the time has been scaled, and we're also going to scale their amplitude. So we multiply each one. We multiply the one that's scaled by 4 to the n by the nth power of 3/4. Okay. So we shrink them while we're squeezing them in. We also shrink them. Okay. And then we add them all together. Okay. So that will be our function. Okay. So f of x, our candidate, will be the sum of 3/4 to the n, phi 4 to the n x, as n goes from 0 to infinity. Okay. Okay. And just make one observation that phi has this property, that phi of s minus phi of t is less than or equal to the size of s minus t. Okay, right? Right. Does that? I hope that's. I'll let you prove that. I hope that's believable, right? The slope is 1 or -1, right? In the places where, if you're looking, right? If you're looking, the place. If you're thinking about the places of greatest change, right? It's basically between integers, right? If you go beyond an integer, the slope is the slope of secant lines are just going to get smaller, right? So the greatest change occurs, between integers, right? And you see that there the slope is -1 or it's +1, and so you have this sort of relation, right? Right. The change is going to be less than, the change in position is going to be less than the change in time, okay? Because the slope is in magnitude smaller than 1. Okay. Okay. So this is so-called Lipschitz continuity. It's a continuous function. In particular, it's a Lipschitz continuous function. I think on your exam, I asked you to show that such functions were uniformly continuous, right? So in fact, this is uniformly continuous. But in any case, all we need is that they're continuous. Okay? Okay, so, okay, everybody okay so far? We're just constructing the function. We take this guy, and then we add together scale copies, copies of it that are scaled in 2 ways. Okay? Okay, so, is this function continuous? Grace, you're nodding your head. Why?
Yeah, because the distance, or I don't know, just like
I mean, I'm sorry. This function. Is the sum function continuous? This function, yeah, we just said it's continuous.
Oh, yeah.
These guys are definitely continuous. What about when we add them? When we take the infinite sum, Josh?
Isn't that the sum also be continuous?
I'm sorry, I can't really hear you.
Oh, isn't that the sum also be continuous? If you just sum together all the continuous functions, then it will also be continuous. Oh, sorry. Isn't that if we just sum together a bunch of continuous functions, it will also go get a continuous function?
Well,
Or does it not hold for?
not, so you can't, so remember, so we're going to have to use something that we just did, actually. So what we need is for this series to be uniformly convergent, right? So if it is, so if the series is uniformly convergent, then we'll have a uniformly convergent series of continuous functions. And that will be continuous, but not otherwise. Then yes. Okay. So what we need to use is Weierstrass's m-test. Okay. This you might have forgotten. It says that if we can get bounds on each of these summands, and then the sum of the bounds converges, then this thing is uniformly convergent, right? By the Cauchy criterion. Okay, so fortunately we can, right? We see that 3/4 to the n. The size of this, right? The size of this is smaller than 1, right? And so we see that we get bounds of just 3/4 to the n, right? And since summation 3/4 to the n converges, Weierstrass m-test implies that this thing is actually continuous. Oh yes.
So would that mean that you can scale it by any number less than 1?
Yeah, that's right. So we could actually, this 3/4 doesn't really matter. Right. As long as we take some ratio, as long as we take some powers of some number less than 1, that's it. Okay. 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 So yeah. So this thing is continuous, and now we want to show that it is non-differentiable everywhere. So there's no point where it's differentiable. Okay. So here's the idea. So our claim now is that f is nowhere differentiable. Okay. So let's pick an x. Just pick any x in R. Okay. Pick some point. Okay. And then we're going to do something interesting, which is for each natural number, we're going to create a little step. Okay, we're going to create a little like a difference. Okay, so we let delta sub n be plus or minus a half times 4 to the negative n. Okay, where the plus or minus is chosen so that there is no integer. There is no integer between 4 to the n and 4 to the n x and 4 to the m x plus 4 to the n delta n. Okay, so the idea here is that suppose this point here is 4 to the mx. Okay, 4 to the mx. Then we look at 4 to the mx minus a half, 4 to the mx plus a half. Okay, right? This length is 1. Right? So we choose, there can only be one integer inside here, right? There could be integers, at each point, but we choose, that's fine. In that case, you just choose either one of them. But at most, there's one integer in between, right? Because if there's an integer here, there's no integer over here, right? The next integer would have to be, distance 1 away, right? So, there can only be one integer in the open interval, in the open half place here, right? Okay, so you choose the plus or minus depending on where the integer isn't, right? To ensure that there's no integer over here. So if the integer is over here, in this case, we're going to choose delta to be negative a half times 4 to the negative half. Okay. And of course, if 4 to the m times x is an integer, then it doesn't matter. Neither side will have an integer. Okay, so then what we want to see is that our main claim is the following, that then if we look at the slope of the secant line, then look at the slope of the secant line using that distance. Okay, so we've got our x, right? We've got our x, we have our x plus delta m, and what we're saying is that the size of that difference is big, is greater than a half times 3 to the m plus 1. Okay, this would require a bit of work. So if you're thinking, why is that true? That's fine. We will explain that in a second. Okay, but you see why this causes trouble, right? For every natural number, we have this delta m, and these delta m's are getting smaller and smaller in size, right? So we've got a bunch of things that are shrinking by powers of 4, right? Things that are shrinking by powers of 4, and as we look at the slopes of the secant lines, the slopes are increasing like 3 to the m, right? So could we be differentiable at x? No, there's no way we could be differentiable at x, right? Because for this to be differentiable, we want this limit, right? We would like this limit to exist, right? As h goes to 0. But as h tends towards 0, we're going to run over an infinity of these delta m's, all shrinking smaller and smaller, while the magnitudes of these are increasing like 3 to the m. Okay? There's no way that this function is differentiable at x. Right? That limit does not exist. Okay? Okay, so now let's work this thing out. Okay. So this turns out to be, it's not too bad. It's a little bit gory, but it's not too bad. So let's think. Let's consider this thing is at this slope of the secant line. Okay. So just by definition, what is this going to be? This is going to be summation 3/4 to the n, right? N from 0 to infinity. Phi of 4 to the n times x plus delta sub m minus phi of 4 to the n x. Right? Everything divided by delta n. Right? That's just the definition. That's just the definition of our function. Right? We're evaluating it at right? X plus delta m minus x. Okay. Right. And we're allowed to combine the sums because of the uniform convergence. Right. Okay. So, okay, everybody all right? Yeah? Okay, great. Okay, so now we make some observations. So observe. Suppose that in the case that n is strictly bigger than m, what happens? Can anyone see what, so what happens? We're going to look at, sorry. So let's consider, call this thing, let's call this thing delta sub n, okay, as n, I'm sorry, gamma sub n as n ranges from 0 to infinity, right? So this is this thing, the secant, the slope of the secant line for this part of the scale, the time scale function. Okay, so let's consider gamma sub n. Right, when n is bigger than m, what happens? Well, the size of this delta m is a half, right? I'm sorry. It's a half times 4 to the negative m, and then when we multiply that by 4 to the n, we're going to get some power of 4 times a half, right? Right. This thing here. Remember, delta sub m is plus or minus a half times 4 to the negative m. Then we multiply that by 4 to the n. So we get 4 to the n minus m times a half, right? Where n is strictly bigger than m. Right? So we get some power of 4 times a half. We get some multiple of 2. Right? So this is, the size of this thing is some multiple of 2. 2 times L. Right? For some L in the natural numbers. Okay. So, so what do you see? We get, this is going to be phi of 4 to the n x plus 4 to the n delta m minus phi of 4 to the n x. Well, this is some multiple of 2, right? So what? Remember that our phi was chosen to be periodic of period 2, right? Our phi was defined by taking this function defined on -1, 1 and extending it to be a period 2 function, right? So if we're adding on 2 here to it, then this thing here is just going to be phi of 4 n x, right? So we get 0. Because all we did was we added some multiple of 2 to it. Well, the thing has period 2, so that's equal to that. Okay, so this is 0, right? And this is actually a finite sum. This is a finite sum. It actually only goes up to n. Okay, because when n exceeds that, then we get zeros here. Okay. Okay. Now, let's say for n equals m, what happens? What happens in that case? We're going to get phi 4n x plus or minus a half, right? Plus or minus a half minus phi phi for n x, and then divide by plus or minus a half times 4 to the negative n. Right? And remember, we're taking the absolute values. Sorry. Okay. So what happens then? Remember that we chose the deltas so that there's no integer in this interval between 4nx and 4nx plus delta sub n, right? So there's no integer inside there. That means that it's either slope 1 or slope negative 1. Yes? Right? Yes? Okay, right? Right, we chose the delta sub m so that there's no integer between these two values, right? That means that, right, so here's 4nx, here's 4nx plus, delta sub n, right, delta sub n, okay. There's no integer between here, right? So that means that we must remember what our function looks like, right? It looks like this, right? So 0, 1, 2, 3, 4, and so on and so forth, right? There's no integer between us, so we know that we're inside one of these intervals, right? So it's either slope 1 or it's slope negative 1, and so we get the top is a half, and the bottom is a half times 4 to the negative n, and so we get 4 to the n, right? Okay, so that's the case. N equals m. I bought new chalk, but I'm destroying it rapidly. I bought 3 boxes of the good chalk for this class. Okay. Okay. Now the last one is n less than n. Okay, so same sort of thing. We have b for nx plus or minus. Plus 4n delta sub m, right? Minus phi for nx divided by delta sub m. Right. Okay. And humor me by allowing me to put to multiply by 1. So I'm going to multiply by 4 to the n over 4 to the n. Doesn't matter. Okay. Okay. Now remember what we said about our function. It's Lipschitz continuous, right? It's Lipschitz continuous, so we know that the top is controlled by just the difference of the arguments, right? So that's just going to be, you see that we get 4 to the n, and on the top we're going to have 4n delta sub n, and on the bottom we also have 4n delta sub n. So by the Lipschitz continuity. Okay. And so we get this is smaller than 4 to the n. Okay. Okay, so that's what we have. That's what we have at this point. So right, when n is bigger than m, we get 0. When n is equal to m, we get 4 to the n. And when n is less than m, we get something less than 4 to the n. Okay. So now we come back over here and we look at the slope of the secant line again, right? So this thing again is just a sum up to m, right? And so if we separate this, I'm going to write this. So this is going to be, I'm going to write this like this. So let me take off the top term, right? The n equals mth term is going to be, right, 3 over 4 to the m times 4 to the m. Right? That's my top term, right? Using this thing here. Right? Okay. And I'm going to observe, so that's of course just 3 to the m. Right? That's the top term. Okay, so we get something like this, plus summation n from 0 to m minus 1, 3/4 to the n times gamma sub n. Okay, just write it like that. Okay. Now, this term is of course 3 to the m. And the biggest that these guys could be is 4 to the n. Right? The biggest that these guys could be is 4 to the n. Right? So by the reverse triangle inequality, this thing is going to be bigger than the difference of this and the sums of these guys. Okay. So this is going to be bigger than 3 to the m minus summation n is n minus 1. Remember that the biggest that these things could be, these guys are all smaller than 4 to the n. Okay, so the biggest that this term could be is 3 to the n. Right? The biggest that this product could be is 3 to the n. I'm going to subtract off the biggest things that you can get here. Right? And that's going to be smaller than this thing. Right? That's the reverse triangle inequality. You know, this plus this is definitely bigger than this minus the biggest thing that this could be. Okay. Okay. Well, that gives it to us. That is our 1/2 3 to the n plus 1. Okay. Using the geometric, it's the sum of the geometric series. Partial sum of the geometric series. Okay, so that gives it to us. That is the first example ever of no, it's not the first. It's an example of a continuous nowhere differentiable function along the lines of Weierstrass's first example, which actually used cosines instead of absolute value functions. But you can imagine how it could be done, right? Because the cosine is also a 2π periodic function. You're going to scale it. You're going to add them together. You're going to end up with boundedness. Okay, so this is an example of you got these functions. They are, they're continuous. They're differentiable, except at some very, blips, just brief moments of time, and you add them together in a uniformly convergent way, and still you end up with something that's that you end up with this thing that is nowhere differentiable. Okay. So, okay. Any questions about this? Any questions? I don't know. I hope this was enjoyable. Was this enjoyable? It's kind of cool, right? The first, I think this is the first example of a fractal, right? Or Weierstrass's was the first example of a fractal. And of course, very hard to visualize until you have computers. Is this cool? Yes, nod your heads. Humor the professor. Yes, Tejan.
If you were to graph this, what would it look like?
If you graph it, well, I just think, you start off with this function, right? Start off with this function, right? And then you add on let's see, this function, this function, right? So basically, you're taking something spiky, and then you're adding on a second level of spikes to it, right? You're adding on a second level of spikes to it. So it's going to be, right? You're going to have this original thing, but you're going to have additional spikes on top of that, right? Right, and then you're going to scale by 4 again, and each of these humps is going to have two bumps on it, right, and so on and so forth. Kind of like the Cox snowflake.
It's like if I put it in Desmos and I kept zooming in, no matter what, it's still be spiky.
That's right. No matter how much you zoom, it's still spiky. You probably you know this example of the Cox snowflake, right? I don't know how to pronounce this. Right, where you start off with something like this, and then you iterate, right? But you say, okay, I'm going to take every interval, I'm going to replace with a copy of this scaled down, right? So I replace this thing with a copy of it. I replace this thing with a copy of it. I replace this thing with a copy of it. I replace this thing with a copy of it, right? And then you iterate. You say, okay, now I'm going to replace every segment with a copy of this, right? Or no, with a copy, again, you just do the same thing. You replace with a copy of that original thing. You keep on going, right? And you end up with something with, with infinite length, right? Because every time you do this, you increase the length by 4/3, right? So you end up with this thing of infinite length. It's a fractal. It has some fractional dimension. Okay. Okay. So that was a kind of a digression. Really, our story is about uniform convergence at this point. So let's get back to the idea of uniform convergence. Right. So. Our story is really about, we like uniform convergence. We would like to be able to find uniformly convergent functions, sequences of functions. Okay, so the goal right now is to create something like sequential compactness. To obtain some kind of sequential compactness. Okay, so you remember that if you have a compact set and you have an infinite sequence in the compact set, then you're guaranteed a convergent subsequence. Right. So that's something that we saw before. An infinite sequence in a compact set has a convergent subsequence. Okay, so we would like something like that, but for function spaces. Okay, we would like to be able to say, I've got a bunch of functions here, and they all satisfy something. I want to find something that they converge to, right? I'd like to have something that they converge to. Am I guaranteed a uniformly convergent subsequence for my functions? Right. Okay. So that is basically the goal for the next 2 classes, to create a theorem that guarantees us the existence of a uniformly convergent subsequence of functions. Okay, so Okay, so in order to do that, we're going to introduce some new concepts. Let me start from here. Okay, so first idea is boundedness. Right? Like just like we're basically trying to make some sort of analog for like closed and bounded, right? When we talked about points in Euclidean space, right? We said, oh, we've got closed and bounded. If we've got a closed and bounded set that is compact, then you're guaranteed this. Then you're sequentially compact, right? So you'd like to do something like that for functions. What should it mean for the functions to be bounded? Okay. So we have a couple of different ways of different notions of this. Okay. So here we go. Okay, so we're going to start off with these two different ways of thinking about boundedness. So you have a sequence of functions. On a set E. Okay. And these are complex value functions. We've got complex value functions on set E. And so we start off with the following definition called pointwise bounded. So if for each x in E, fnx is a bounded sequence. We say that the sequence Fn is pointwise bounded on E. Okay, so right, so what this is saying is that if you take any point x, if you take any point x and you look at all the fnx, that's going to be bounded. Okay. So another way of saying this is that equivalently, there exists a phi going from E into R such that phi nx is bounded by, fnx is bounded by phi of x for all n. Okay, let me ask you this, to see if this makes any sense to you. If these guys are pointwise bounded, do I know that each one of them is a bounded function? Turn to a neighbor and say, what? So I've got some, if I know that some f sub n is a pointwise bounded sequence, does that imply that the first guy is a bounded function? That one of them is, any fixed one of them is a pointwise bounded, that is a bounded function? And the answer is no. The answer is no. We don't, that it doesn't imply that, right? All it says is that if you consider a single point, if you consider them point by point, okay, if you consider these values, right, at specific points, so like I consider all these values, I choose some x naught, and I look at the values f sub n as n goes from 1 to infinity. I know that that's bounded. Okay, I know that that's bounded. Okay, so I know that for each point, there's some bounds that I can create. Right, some phi is negative phi. Right, I know that for each right, I know that for each point, I can create a bound of values at that point. But it doesn't say anything about how each individual function behaves over the whole set. Okay, so that's what this equivalent formulation is to make clear, right? What it's saying is that, look, you're going to have some function phi. Okay, you have some function phi, and you know that for every x, all the values lie between phi and negative phi. Right? So here's phi, here's negative phi, right? And you know that at each point, all the values of the f sub n's lie between these two things. But that phi could head off towards infinity. Right? Okay. So it doesn't, and you don't know anything about the boundedness of each individual function. Okay, you know boundedness at a point. Okay. So maybe it's more clear to call this thing like point by point boundedness, point by point bounded. Anyway, if that's helpful to you. Okay, I'm going to erase this picture. Okay, second kind of boundedness. So if there exists an M such that fnx is less than M for all x in E and for all n 1, 2, 3, etc., then we call the f sub n uniformly bounded. Okay, and you see that being uniformly bounded is much stronger. It's a stronger idea than being pointwise bounded. Because what this is saying is that there's an M, right? There's an M, and all your functions live between these two bars, right? So it's not only is there a function phi that works, but that function is a constant. Right? The phi that works, you can take your phi to be a constant, and your guys live between those bars. Whereas over here, right, your phi just had to be a function, right? just had to be a real valued function, right? So, your functions had to live between these bars, but the bars could go crazy, right? Here the bars are uniform. Okay, so that's uniformly bounded. Okay. So we're going to first talk about pointwise convergent subsequences. So remember what our goal is. Our goal is to, put some conditions on our function so that we're guaranteed convergent subsequences. Right? We're trying to find conditions that guarantee convergent subsequences. Our first goal is to find conditions that guarantee pointwise convergent subsequences. Okay, and then our second goal will be to find conditions that guarantee uniformly convergent subsequences. So this is it's going to be kind of a long haul. Okay, so get ready for kind of a long proof. The next 2 days will kind of link together. I should say the best time I had in teaching a math class was in the Fourier analysis class, where I proved, at the end of it, we prove a number theory result using Fourier analysis by Dirichlet. And that actually took 4 lectures to get there. So yeah, it was fun for me at least. I don't know how it was for the class. Okay, so basically we're trying to answer this question: under what conditions do we have, are we guaranteed a pointwise convergent subsequence? This may be why every time I offer to teach Fourier analysis, my department gets upset. Okay, so okay, so here's the first. Here's the first question, and the answer is no. Okay, so if you have some uniformly bounded continuous functions on a compact set, does there exist a pointwise convergent subsequence? And the answer is no. Okay. I'm just going to put up the example. I'm not sure if I should do this, but the example that's given in the book. So the answer is no. Rudin gives a counterexample that looks like this. He says, well, look, consider fn of x being sine of nx on the interval 0 to pi. Okay. Okay. He says, well, look, if some subsequence converged, then you would know that for each point, the limit of sine of nkx minus sine nk plus 1x is 0 as k goes to infinity. Okay, so Rudin gives this example. He says, well, look, if you had some subsequence, right, sine n sub k x, and suppose that thing converged pointwise. If that converged pointwise, then the limit of this thing would be 0, right? Is that okay? Right. That's just right. This would be right. This would be a Cauchy sequence, right? And so the difference is going to go to 0. Okay. If that's true, sorry, I'm just going to, if that were true, then the limit of the square would also be 0. Right? Because you just multiply the limits together, and you get the limit of the square. Okay. Okay. Now, if that were true, then that would imply that the limit of the integral as k goes to infinity of this limit, I'm sorry, of this thing would be 0. Okay, and this is by the dominated convergence theorem. So I had you guys read the dominated convergence theorem in the homework, right? So it basically says that if you have some functions that converge pointwise, and they're sort of dominated by some integrable function. They're dominated by some integrable function. Then you can change the order of limit and integration. Okay, so you see what happens here. The limit of, because of dominated convergence, the limit of this integral would be integral of the limit, but the limit is 0. Right? If this were true, then you could change the order, and you would get 0. Okay, right. But if you work it out, in fact, this turns out to be, but this integral is actually 2 pi. So if you work it out, if you actually multiply it and do your calculus integral, then you get 2 pi. Okay. You don't have to worry too much about this. This is just an example, right, showing you that it's not so easy to get a pointwise convergence subsequence. Okay, so like you know, even if you've got continuous functions, they're on a compact set and they're uniformly bounded, right? Still, you're not guaranteed a pointwise convergence subsequence. That's the moral here. More than the example itself, but just this moral that even slamming on all these conditions isn't enough to guarantee you pointwise convergence. Okay. Okay. What we can do, and it's not that impressive, is the following. So here's some sort of weak result. So we can obtain a kind of weak result along the lines that we're hoping for. Okay. So it goes like this. If you have a bunch of, again, a sequence of complex value functions on some set E, and if E is countable, and the sequence is pointwise bounded, then you guarantee a pointwise convergent subsequence. Then there exists a pointwise convergent subsequence. Okay, but this you see is it's kind of a limited theorem, right? Because you have to deal with a set that's countable, right? A countable set. That's you don't have that very often. Okay. So the idea is that we're going to use actually something like Cantor's diagonal process. Okay. So the strategy is to use the diagonal process. Okay. So here we go. Yeah. Okay. So let's put on some notation. So let's notate E is going to be just a collection of the xi from I from 1 to infinity. So we have these points, right? It's countable set of points. Okay. Okay. And we observe, right? These guys are pointwise bounded, right? The functions are pointwise bounded. So in particular, right? If we look at all the values at a single point, those values are going to be bounded, right? As n goes from 1 to infinity, is bounded, right? So we have this sequence of points, right? We have the sequence of points, right? And they're bounded, right? F1, x1, f2, x1. Et cetera, et cetera. There's infinitely many points between some bounds. Okay. Okay. So we're guaranteed then that there exists a convergent subsequence. So there exists a convergent subsequence, right? Because we've got an infinite sequence in a compact set. So there's some convergent subsequence. Let's call that convergent subsequence f sub n k x1 as k goes from 1 to infinity. Okay, so let's now notate f sub 1 comma k as f sub n k. Okay, so we have these guys that converged. These functions converged on x1, right? So we're going to notate them as this is the one indicates that these functions converged on x1, and the k indicates that it's the kth element of the subsequence. Okay. Okay. You know that things are going to get bad when the notation starts getting bad like this. Okay. So. Don't worry, it won't last. It's only going to be bad for a little bit, but yeah. Okay, so then you iterate. Okay, so we take these guys now. So we take these guys f1 n at x2. Okay, and we look at the guys as n ranges from 1 to infinity again. If you want, you can write k, but I'm going to need a k in a second, so I'm going to call it n again now. Okay, it doesn't matter. I'm just relabeling. Okay. So we look at, these are the guys that already converged on x1. Now I look at that subsequence's values at x2, right? Well, by the same reasoning, there's going to be, those are bounded by the pointwise boundedness, and so there's going to be a convergent subsequence of those guys, right? So since this is bounded, again, there exists a convergent subsequence, which we're going to call, it'll be f1 n sub k x2, as k ranges from 1 to infinity, right? So the n changes to the n sub k again, right? You get a subsequence. So these are the guys that converged at x2. But they're a subsequence of the guys that converged on x1. Right? So these guys converge on x1 and x2. And you can imagine what's going to happen. Right? So let's notate, as you might expect, we're going to notate f2k as f1 n sub k. Right? So these are these are the functions that converge on x1 and x2, and this is the kth element of that subsequence, just as before. Okay. So in this manner, we construct our f11, f12. So here's our first sequence, right? Here's our first sequence, the guys that converge on x1, etc. Right? The guys who converge on x2 and x1. Right? The guys who converge on x3 and x1, and so on and so forth. And so on and so forth. Right? And right? And notice that one remark that each row is a subsequence of the row above. That the nth row converges on x of n, right? And that the kth element in the nth row is in the bigger than kth place in the prior row. Right? Each row is a subsequence of the former row. That's obvious. The nth row converges on x of n. That's also obvious. The kth element, right, in the nth row is in the bigger than kth place in the prior row. I hope that's clear, right? Because this is a subsequence of the previous one, so its kth element is going to be past the kth element up here. Okay. So what are we going to do? How are we going to create our? Remember what we want. Right? Recall we want a pointwise convergent subsequence. Right? In other words, for each point in E, we want some subsequence that f sub k, sorry, f sub n sub k or something should converge. Right. We want to be able to say, if you choose any point, then we can get then this thing is going to converge on that point. Right? So what are we going to do? Anyone see how we're going to choose our subsequence? Right? These guys converge on x1, these guys converge on x2 and x1, these guys converge on x1, 2, and 3, and so on and so forth. Right? So, anybody wants to say it? You're shy? You're afraid that somebody will say, it's like me saying Weierstrass. The answer is, you take the
Nth row?
well, the nth row is just going to converge on the first n points, right? So if you choose any row, that's not going to work out. The jth column. I don't think that'll work out. But what's the only other thing we could do? We're not going to go this way. We're not going to go that way. We're going to go diagonally, right? Right. So right? Cantor's diagonal argument, right? So we go diagonally, right? So then f sub nn xk converges for each k, right, as n goes from 1 to infinity. Okay, right? You think about it, right? Like, if I take the diagonal and somebody says, does that converge on x1? Well, you'd say, well, look, this thing converges on x1, and each of these guys is higher up than its actual position, right? It's either at its actual position or it's at a higher position, right? So this is actually going to go faster than that first row, right? Or at worst, the same speed as the first row, right? So it does the same thing as the first row, but either at the same speed or faster, right? So yes, this basically duplicates what happens in the first row, right? What about the second one? Same comment, right? Same comment, right? If I take this diagonal, well, from here onwards, we're basically doing what happens in the second row, right? But just at a faster or equal speed, right? And so on and so forth, right? Whatever point you choose, if somebody says, what about the billionth point? Well, you just go down to there and you say, well, look, you know, if I start at the billionth guy here, then I know that, I'm going to duplicate what happens in that billionth row, you know, from here on, from here downwards. Right? Okay, so I leave it to you to write that out more rigorously, but that's the idea. Okay, so so each of these things converges for each point individually. Okay, and this proof, although I said this was a weak result, this is actually going to be a fundamental step in the proof of the theorem of Ascoli-Arzela, which is kind of the climax of this section that we'll get to next time. Okay, so that's it for today.